Hi, my name is Kristyn Albrecht. I'm in my final semester of my undergrad for mathematics with data science specialization. I'm also doing the accelerated master's program at SDSU. So I'm working on my master's in statistics and I have about 1 year left of that. So now let's begin with my presentation. Let me go ahead and share my screen. So for my senior capstone project, I did an analysis of New York City complaints using multinomial logistic regression advised by Dr. Fan. So here's a little overview of my presentation and my senior capstone project. So first, I'm obviously going to start with a little bit of a background, and then I analyzed New York City complaint data to explore different frequencies within the data relating to crime and the profile of the victim and the suspect. And then I used multinomial logistic regression to model the probability that a certain individual based on their race, sex, and age will be the suspect of a certain crime. And then I explored an explanation of my results. Here's a little bit of a background. So this year for senior capstone, we all had the same general topic, which was crime statistics, which I was really happy about because I've always had an interest in crime. So it was a great topic for me. And I love crime podcasts like Crime Junkie. And I grew up watching Dateline with my mom. I also ended up using New York City complaint data because I always have had an interest in New York and crime. And then last semester in senior capstone 1, we spoke a lot about white privilege and diversity in the classroom, as well as diversity in the workplace and discrimination that people of color experience or that females experience, things like that. And so I wanted to translate those topics from senior capstone 1 into my senior capstone final project. And then that mixed with my interest in the Black Lives Matter movement this past summer just made me that much more excited about this topic. And so I just wanted to explore the discrimination that people of color experience. And so a lot of the discrimination that people of color experience or females experience, young people experience are from implicit bias. Everyone has some form of implicit bias, and implicit bias are stereotypes that are completely unconscious to us. We don't actively realize that we think this way, but they influence our reactions, our feelings, and our decisions. One example of implicit bias is assuming that like a female is a lot weaker or not as smart as a male, or a very large link is the link between African Americans and crime. In a 2010 survey, the right response of the survey overpredicted the number of robberies, illegal drug sales, and juvenile crime committed by African Americans by 20 to 30%. Another 2010 survey, a telephone survey that was done in Florida, found that the respondents believed that 46.4% of violent crimes were committed by African Americans, where the actual percentage was only 21%. So our first examples show us that juvenile crime, young people, are discriminated against for how often they are to commit a crime, and additionally, African Americans. Our second example really just shows us that race plays a factor in how people think of who people think will commit certain crimes. And this last example shows us both race, sex, and age, which is why these three variables were used in my multinomial logistic regression. So a study in 2004 found that among drivers under 25 years old, 28% of African American males have been stopped for a traffic stop. And it wasn't just a basic traffic stop. They were stopped because the police believed that they had some sort of a suspicious behavior, which is why they stopped them. Only 17% of African American females were stopped, and only 13% of white males were stopped. The researchers also found that African American males must be 50 years old or older to have the same probability of being stopped for a white male under 25. So here we can see that being a young African American male increases your chances of being stopped by the police. So I used the idea of implicit bias and those types of conversations for the main goal of my senior capstone project. So this was to model a probability that a certain individual based on their race, sex, and age will be the suspect of a certain crime. Race, sex, and age were used since these variables are things that people face the most discrimination for. In fact, if you even Google discrimination, it comes up like the unfair treatment of someone on the basis of race, sex, and age. So it's very legitimate thing that people experience discrimination for. And so I'm going to use my model to determine if one can really accurately predict the suspect of a crime based solely on race, sex, and age. Within my data set, race and sex were categorical values, and age was also a categorical value because it was an age group, which definitely makes sense. If someone were to report a crime, they might not always know the exact age of the person. So they have an age group like 18 to 24, less than 18, older than 65, things like that. And so since I had two or more predictor variables and a dependent variable with multiple levels that were categorical, and then different levels were the different crimes, a multinomial logistic regression was the best choice to model my data. So let's begin with my data collection. As I mentioned, I've always had an interest in New York City. And so I found New York City complaint data that had all the complaints in New York City from 2016 to 2019. And I used complaints instead of arrests because I thought this would be a lot more telling of the discrimination that people experience on the basis of race, sex, and age, because the arrests might not actually match what someone will assume commits a certain crime. So if you're calling the cops and you don't know exactly who committed a crime, but you just, oh, well, I'm just going to assume it was a young person of color, that it's a lot more telling. So that's why I use complaints instead of arrests. And so this include all felony, misdemeanor, and violation crimes reported to the NYPD. So then I clean the data. Columns relevant to my analysis removed. So location of the crime, time of the crime, special codes that the NYPD uses. Then I removed all rows with any NA value. I thought this would be the simplest route just to completely remove them. Then I checked to make sure that we had no duplicate values, which there were none. And then any data values that did not make sense were excluded. So this was like typos, ages over 100 or below 0, and sex identification listed as E. And I wasn't sure if maybe that was just something I wasn't familiar with, but I did look it up and I couldn't find anything, so I did end up removing that value. And then lastly, I converted category values to factors before performing my multinomial logistic regression. So as I mentioned, for the multinomial logistic regression, we have different levels, which were the different crimes. And for those different crimes, I used the top 3 crimes amongst the suspect category. And so I used the top 3 crimes for amongst the suspect. So I wanted to look at the most common complaint in all of New York City. So the bar plot to the right shows us the most common complaints. And so number 1 was larceny, which is stealing property that is over $50. Number 2 is harassment 2, which is committing an act to alarm or seriously annoy another person for no legitimate reason. And number 3 was assault 3 and related offenses. And this is physical injury by means of a deadly weapon or dangerous instrument. The next analysis was finding the most common complaint amongst people's sex, race, and age group for the suspect as well as the victim. So here we can see that the most common complaint was harassment 2, and it was for African American males between the ages of 25 and 44. So that was our most common suspect, and the most common complaint for the most common suspect was harassment 2. And then I also wanted to note that the N is for the frequency. So this is how many times this showed up in my data. And so here are the results of the most common complaint for the victim. So I thought it was very interesting that the most common suspect was an African-American male between the ages 25 and 44, and the most common victim was an African-American female between the ages of 25 and 44. I think this is very telling of the discrimination that people of color experience, that the most common suspect would be a person of color, and the most common victim would also be a person of color. So before diving into my multinomial logistic regression model, let's first look at the assumptions. So the first assumption is that the dependent variable is a categorical value with 2 or more levels, which is what we had, a categorical value, which were the offenses, and the multiple levels were the different crimes. Then we also need 1 or more independent variables that are either nominal, continuous, or ordinal. And so I had nominal independent variables, which were the race, sex, and age. And we have 3 of those. And unlike a normal linear regression, a multinomial logistic regression does not assume normality, linearity, or homoscedasticity. However, it does assume no multicollinearity. And so this occurs when 2 or more independent variables are highly correlated. So here, looking at our variables, we can see that none of them are highly correlated. They're all their values are around 0. So we met all the assumptions of the multinomial logistic regression. So we know the model is valid. Now we just have to look at if the 3 independent variables that we used were enough to predict if someone was going to commit a crime. So as I mentioned, the top 3 complaints in the most common suspect category were used. And so it was harassment 2, assault 3, and related offenses, and offense against public order, sensibilities, and the right to privacy. So we already defined harassment 2 and assault 3 and related offenses. So now to define offense against public order, it is kind of a blanket term for just calling the cops about something that just seems out of the ordinary, something that's just not normal, something that seems suspicious. You can just call the cops and say, oh, there's someone like outside my apartment. I'm not sure what they're doing. So it's kind of a blanket term for all of that. And so those were used for my multinomial logistic regression. So for this regression, the odds of being in a different outcome categories is in reference to a base group. Here, the base group used was assault 3 and related offenses. So we're gonna see it's gonna compare the log odds of the offense being harassment 2 versus assault 3 and related offenses, and the log odds of the offense being offense against public order versus assault 3 and related offenses. So we have that bit of a comparison. And then additionally, since race, sex, and age have multiple different levels, race, we have many different races, ages, we have many different ages, and for sex, we have male and female. We're also going to see the same type of comparison, which we will see later in the presentation when we interpret our different coefficients. So a multinomial logistic regression is an extension of a logistic regression. So a logistic regression, we have a binary dependent variable, so a yes or a no, or a pass or a fail. But when we have a multinomial logistic regression, there are 2 or more dependent variables. So date, time, place, slow, fast, quick, and for our example, the 3 different crimes. So if we have P, which is a probability, then P divided by 1 minus P is the measure of the likelihood of a particular outcome referred to as the odds. Taking the log of the odds results in the log of P over 1 minus P, which is called the logit function or the log odds. For a multinomial logistic regression, the logit function serves as the depending variable, which yields this following. And so we have the log odds, logit of P, log of P over 1 minus P, just the different ways that we can describe it. And so that is equal to beta naught, which is our intercept, plus beta sub 1, which is the coefficient related to the independent variable. So beta sub 1, x sub 1, or x sub 1 is our independent variable. And then plus all the way to beta sub s minus 1 and x sub s minus 1. And so if we do e to the power of beta naught plus beta sub 1, x sub 1, plus all the way to beta sub s minus 1, x sub s minus 1. And then if we have that 1 divided by that, we get the following equation for P. So that's just from taking it e to the power of this here. And then if we rearrange it a little bit, we get P, this following equation here. And then using matrix notation, P can very easily be derived. So our outcome is going to be in this following format. So the log odds of the offense being harassment 2 versus assault 3, which is equal to beta naught, our intercept, plus beta sub 1, which is the coefficient related to the age groups, the different age groups we have, then race, and then sex, and then epsilon is random error. It's not going to be perfect every single time, so we always have to add the epsilon at the end to represent our random error. And so that's going to be our model 1. Model 2 is the log odds of the offense being offense against public order versus assault 3. Beta naught, our intercept, beta sub 1, the coefficient related to age group, all the same there, plus epsilon, our random error. Now, to make things a little bit easier, we're going to say the probability of the offense being harassment 2 is going to be P1. Probability of the offense being assault 3 is going to be P2. And probability that the offense is offense against public order is going to be P3. And then additionally, the age groups, which are 18 to 24, that's going to be group 1. 25 to 44 is group 2. 45 to 64 is group 3. And 65 plus is group 4. So this is the resulting model with each number rounded to 2 decimal places. So now let's look into an interpretation of our coefficients. So jumping back into an interpretation of Model 1's coefficients, so the log odds of the offense being harassment instead of assault 3 will increase by 0.95 if moving from age group less than 18 to age group 65 plus, so group 4, remember, was 65 plus. The log odds of the, so now looking at the race, the log odds of the offense being harassment instead of assault 3 will increase by 0.08 if moving from race equal to American Indian / Alaska Native to race being white, and the log odds of the offense being harassment instead of assault 3 will decrease by 0.40 if moving from female to male. Now remember, the reason that we interpret the coefficients this way is because the race, sex, and age all had many different levels. Race had all the different races, age had all the different age group, and sex had the male and the female. So now looking at Model 2, the log odds of the offense being offense against public order instead of assault 3 will increase by 0.73 if moving from age group less than 18 to age group 65 plus. Now looking at race, the log odds of the offense being offense against public order instead of assault 3 will increase by 0.17 if moving from race equal to American Indian / Alaska Native to race equal to white. And the log odds of the offense being offense against public order instead of assault 3 will increase by 0.52 if moving from female to male. So now we have our model, we need to check to see how accurate it is. To find the accuracy, I built a classification table. The classification table separates the data into 4 different outcomes. So true positives, it's when it's predicted to be a success, turns out to be a success. False positive, it's predicted to be a success and it failed. True negative, it's predicted to be a failure, turned out to be a failure. False negative, predicted to be a failure, but turned out to be a success. And so in our case, the true positive is going to be, it's predicted to be this certain crime, it's a certain crime. True negative, it's not going to be this crime, didn't end up being this crime. False positive, it's going to do this crime, and it failed, wasn't the crime. And predicted failure, it's going to be this crime, but it turned out to be another crime. So then we just sum the diagonal elements, and then dividing that by the total observations, we can find the accuracy. The accuracy for my model was 48.68%. So this means the model gives an accurate prediction 48.68% of the time, which is essentially a random guess, like flipping a coin. And so from my exploratory data analysis, as well as the multinomial logistic regression, we have further evidence that people experience discrimination on the basis of race, as well as sex and age. So through my exploratory data analysis, I found that the most common suspect is an African American male between the ages of 25 and 44. Now, African American males actually only make up 24.3% of the population in New York City, yet the most common complaints are against African Americans. So that's just like, those two just don't correlate. And then additionally, the model I built proves that assuming someone will commit a certain crime based on race, sex, and age is just not reasonable. These 3 demographic characteristics are not enough to assume someone will commit a crime. Our model met all the assumptions. It was a valid model, but race, sex, and age just cannot be used to predict that someone's going to commit a crime. I think if we had the addition of something like maybe location, income level, education level, things like that could maybe be used to predict it, but discriminating someone using discriminatory characteristics like race, sex, and age will not work, are not enough. And so, as I mentioned, these all come back to implicit bias. People have an implicit bias that a young African American male is going to commit a crime. So when they're asked of who committed a certain crime and they're not exactly sure, their implicit bias just goes back to that link between African American males in crime. So to correct this, we need to become aware of our implicit bias. Everyone has it. It's nothing to be ashamed about, but we need to work on correcting it. When we are aware of it, we can consciously correct it. We can realize that it's something that we're doing and stop doing it. And so another thing we can do is pay attention to examples that challenge our implicit bias. If we assume that a male is more likely to have a position of power like a CEO or something like that, we can find examples where that doesn't work, where that's not true. And we can change our implicit bias And so the input is something positive, like females can be in positions of power. And so we find examples of females who are in positions of power, and that can change our brain and we'll have new generalizations about the CEO of a company. And so every time you realize you're stereotyping someone, make an effort to recognize it and rewire it. So if you automatically are assuming that a young person is going to be louder than an older person, you need to realize that you're doing that and rewire it. Be like, no, that's not true. It's not always that way. And then additionally, bias comes out even more when we are stressed, if we are acting or thinking way too quickly. So in these states, we are less effective at processing new information and we will rely on our unconscious patterns. When you find yourself in these situations, you need to take a step back and slow down so you can think in the best way without relying on biased stereotypes. So here's the conclusion of my presentation today. Many people unknowingly stereotype others based on their race, sex, and age. I made a multinomial logistic regression model for New York City with race, sex, and age as the independent variables, and the top 3 most common crimes as the dependent variables. And we determined that race, sex, and age cannot accurately predict the probability that someone will commit a certain crime. Everyone can practice ways to challenge their implicit bias to decrease their unconscious stereotypes against minorities, specifically when it comes to people assuming a person of color will commit more crimes. Here is my works cited for this presentation. Thank you for listening to my presentation today, and I really hope that my presentation helped you become aware of implicit bias so you can accurately fix implicit bias in your everyday life. Thank you.